Hello everyone and welcome. Welcome to the second installment of this series of adventures in spectroscopy. Let's start with the concept of emission. Every physical body emits radiation. The hotter it is, the brighter it emits. The hotter it is, the bluer the emission is. This is called Planck's law. Here's the man on the left, his equation in the middle, and the equation visualized on the right. Now the equation, we can see it's dependent on temperature as well as wavelength. And this is what we see here. Intensity is dependent on temperature, on wavelength, sorry, horizontal axis, and temperature here. So what we see is a curve, and that curve is a theoretical black body radiation. So a body at that temperature emits all these wavelengths, including visible, which are colored here with visible wavelengths. That includes all these radiations. And as temperature increases, you can see that it gets bluer. This is, the peak is in blue here, and it even goes to ultraviolet. So that wavelength to intensity relationship of light, along with the way that chemical elements react with light, open a world of profound understanding of nature through spectroscopy. Now let's measure some lights. Let's start with tungsten bulbs. Here's the setup again. Here you can see the tungsten bulb. It's a regular car bulb. And let's look at the spectrometer. So this is very similar to black body radiation. It probably has some attenuation in the infrared. Infrared being on the right of 800 nanometers. But otherwise, it's pretty close to a black body radiation. So here are other bulbs that I have measured. That's the basic regular 12-volt car bulb. This is a yellow bulb on cars as well. This is a 12-volt, what's called halogen bulb, regular frosted sphere bulb. This is a flame style clear glass bulb we use for Christmas. This is a floodlight that you use to warm things up. Halogen again in this with a small integrated reflector, it's called an MR16. Halogen in long pencil-like filament. And here is a flashlight, just a mag light with what is called the xenon bulb. All of these look very much the same, except maybe for the orange one where we see the blue and green has been attenuated by the orange glass. And the halogen here, the MR16, we can see that there's less infrared, this part of the spectrum, probably to minimize heating of this bulb. I have a special treat for you. There you go. I've been very curious to see what kind of light the minions are generating. There you go. Minion spectrum. The peaks are probably caused by the plastic, but this is underneath the plastic is a regular little bulb with a tungsten filament. So it's no different than all the other bulbs that we looked at before. All right, let's go with the LEDs. I've added a little piece of fiber optic to the spectrum, to the spectrometer, so that we can read precise sections. This is an iPad, and if I look at the white, you can see the different colors are combined. This is the green portion with the, we can see it on the spectrum. The red portion will show this section here. I think there's fluorescence here. We'll talk about that a little bit later. Blue is here, blue LEDs. This is a combination of LEDs generate these colors that you see, so that's very important. Here we have all the LEDs that I have measured. On the upper left, my iPhone 7 with a white screen. Here a LED strip, 12-volt LED strip. This one is recent, 2020. This one was an old one, yellowed. This one is kind of an older one, 2017. It's also a cool white. This is a 5-watt LED that I've bought that has a sunlight full spectrum, 5000 Kelvin. This is a simple LED in my battery charger. This is a remote control LED. This is a flashlight, UV, with an LED that is used to detect insects in urine. And this is an assembly that I made with 4 different wavelengths of individual LEDs. So when you look at all of these, what you see is, for screens in strips, you see blue LEDs that are associated with a bigger lump here. And this is phosphorus that reacts with the blue light from the blue LED. So if you want green light, for instance, you take a blue LED and you add phosphor that makes it glow in the green. Very similar here. What we see in this case is yellowing of the surface or the wrapping of this LED, which makes the blue go away. Interesting stuff in the remote control, because you don't see this with your eyes. So when you press your remote control, there's an infrared LED around 940 nanometers that is triggered. And one last point on these is this white LED here, very recent, 5-watt, very powerful. It's actually made out of 12 individual LEDs, all combined on this chip with different phosphors. And that combination gives us the smoothest spectrum that we can get in the series of LEDs. And this is the best way to get the most reliable color rendition, is to have a full spectrum LED like this. And the third group, this is a group of laser diodes. Here they are, 10 different wavelengths. Briefly turn them on. So I have 10 colors of lasers: 405, 450, 520, 532, which is a typical green laser pointer. I have 630, which is a typical red laser pointer. This is a 650, 810, 830, 850, and hard to see, but I do have a laser at 980 nanometers. Now, the process to generate light in lasers, in semiconductor lasers, because these are diodes, is a little bit different. In this case, you have stimulated emission from a very narrow semiconductor junction. And if you compare it with LEDs, these are very, very narrow. In fact, lasers generate only a single wavelength. Okay, group number 4, fluorescent. This is the spectrum. So let me explain that via an annotated spectra. And what happens here is, in a compact fluorescent, just like a regular fluorescent light, you have mercury vapor, and that mercury is being excited by the electricity you put in it. And the tube itself is coated with phosphors that then generate the rest of the light. So these phosphors actually fluoresce. That's why it's called fluorescent light. So as a result, you get emissions from mercury here and here, as well as this one. And then you have other elements that are part of the secret recipe from manufacturers. So, but we know there's terbium here and here, and europium at this point. Okay, group number 5. These are various items. First one will be difficult to measure. It's a butane torch. You can see the spectrum in the background. Interesting, complex spectrum. And I had a little bit of salt with the flame, and we can see sodium sparks. All right, let me go to the spectrum itself that I've recorded earlier and explain it. So the butane torch is the upper left spectrum, and its hydrocarbons are burning, and that's why we have like this carbon, these carbon lines here, and also a link carbon and hydrogen. So it's hydrocarbon. I've measured also fondue fuel, which is methyl alcohol, and this is the kind of spectrum I got. I believe this is oxygen here. So it's a blue flame as well, similar to in color to the butane. Lower left, I have tried burning isopropyl alcohol, and I get this closer to a black body radiation. And there's this little peak, same frequency or same wavelength as this one. So it's a different kind of combustion than the fondue fuel. And it's very similar to lighter fuel here, lower right. So others that I've measured include a small neon bulb, very nice amber glow, very complex spectrum as well. And these are the emission lines of the gas neon. Very similar for Nixie tubes. I assume this is neon as well. Burning match, I managed to capture that previously, lower left. And it shows some combustion, obviously, and some peaks. I believe this is oxygen as well. And on the lower right, you have this disinfection light that you can buy for traveling purposes. And it's UV in order to kill bacteria. But in fact, the wavelength is outside the range that I can measure. It's in the 270 nanometers. So it's before the lower range here. But I can still see that light with my eyes. And so there's different peaks in blue and also in green and yellow. All right, group number 6, sunlight. We are currently looking at the sky about 45 degrees away from the setting sun. And as you can see, we have a complex spectrum with a peak around here and the rest of the spectrum towards the infrared with several dips. Now I have added this blue line, which is a black body curve at 5250 degrees centigrade. So you can see that we're pretty far from the shape of a black body. Although the sun is supposed to look at it as a black body, I'm not looking directly at the sun, I'm looking at the atmosphere. Otherwise it would saturate the spectrometer. So this is the same temperature about as the surface of the sun, 5250 degrees centigrade. Let's go into an explanation for these dips. So here's the spectrum of the sun. In yellow, we have the sunlight at the top of the Earth's atmosphere. It's 1365 watts per square meter, a lot of energy. We can see that this spectrum has several dips caused by gases on the top atmosphere of sun. And these dips are caused by hydrogen, sodium, iron, and so on. In gray, we have a black body, a Planck spectrum, at that temperature. This represents the temperature at the surface of the sun. So you can see that the match is not perfect, but it's pretty close. And the peak is at the same wavelength. In red, we have the radiation that we receive from the sun at sea level. This is below 1000 watts per square meter. And it has several dips as well. And these dips are caused by absorption bands in our own atmosphere. You can see in purple the items like oxygen, water here as well, here, carbon dioxide, water. All this changes the spectrum of the sun once it gets to the Earth's surface. You can also see that in different wavelength bands, you have different levels of energy. 3% of the energy is in the UV, 44% of the energy is in the visible, that is what we can see with our eyes, and 53% of the total energy received from the sun is in the infrared. So if you can gather this energy, harness it with solar panels, for instance, it is very significant as far as energy conversion is concerned. Now we're going to look at setting sun. We're going to look at the spectrum of the sky as we did before, but with a time lapse throughout the sun setting. Interesting time lapse here, lasting about 30 minutes. And the sun is actually setting below the horizon at the intensity count of 13,000. So there it is, it's going below the horizon around here. And you can see that the blue and green is more attenuated than the red, which shows why the sky is redder when the sun is set. So, as we saw, the world around us is filled with light, different kinds of light, which can tell us a lot about its sources. So thank you for watching. I hope that you found this video useful, and subscribe to my channel so you do not miss the next installments of this series, transmissions and reflections. Thank you.